You have seen fire 1,000 times. It is one of the most familiar sights in human history. The flicker of a candle, the glow of a stovetop, the roar of a backyard bonfire. We treat it as a basic fact of nature. It's hot, it's bright, and it consumes what it touches. Most people go their entire lives without asking what it actually is, satisfied with the simple observation that fire just happens. But if you stop looking at the flame and start looking at the mechanics of the universe, you realize that fire is not a thing at all. It is a window. It is a rare moment where the invisible laws governing atoms and energy become visible to the naked eye. When you truly dig into the physics of a burning log, you discover a story so perfectly connected to the stars and the air that it fundamentally changes how you see the world. Start with the ingredients. You have a piece of wood, a dead tree sitting in your fireplace. Surrounding it is the air, filled with oxygen molecules floating around. On the surface, nothing is happening. The wood has been there for years. The oxygen has been there the whole time. They are touching, but they are silent. However, at the atomic level, there is a profound tension. The atoms in that wood and the oxygen in the air have a specific relationship. They want to snap together. Oxygen, in particular, is desperate to be next to carbon. If they get close enough, they lock into a stable, low-energy configuration. But here's the problem. Even though they want to be together, they don't know it yet. If they aren't close enough, they actually repel one another. This creates the fundamental mystery of our world. If carbon and oxygen want to snap together so badly, and they are constantly bumping into each other, why doesn't everything just spontaneously burst into flame? Why can a piece of wood sit in a forest for a century without reacting? The answer lies in a hidden barrier. To get to that stable state where they can finally lock together, the atoms must first climb a hill. It is exactly like a ball rolling along a landscape toward a deep volcano crater. The ball wants to be at the bottom of that hole that is the most stable place for it to be. But to get there, it first has to roll up the side of the volcano. If it isn't moving fast enough, it just rolls halfway up the slope and falls back down in the air around the wood. Millions of collisions are happening every single second. Oxygen molecules are slamming into the carbon surface of the log, but they aren't reacting. They hit, they bounce, and they separate. They aren't moving with enough speed to get over that initial barrier. This is why the wood can sit there for decades, existing in what we call a metastable state. It is a system full of potential energy that is stuck because it lacks the necessary nudge. But then you strike a match. You aren't doing anything magical. You are simply providing a small amount of heat to a tiny area. In the language of atoms, heat is not a fluid or a substance. It is jiggling motion. By lighting that match, you are making a few atoms jiggle much faster than their neighbors. Suddenly, those few atoms have enough energy to go over the top of the hill. They move fast enough to overcome the repulsion, and they finally snap together with the carbon in the wood. And when they snap, they release energy. That release isn't quiet. It creates an intense, violent, jiggly motion in the surrounding atoms. This is where the situation transforms from a peaceful coexistence into a catastrophe. The energy released by those first few atoms provides the nudge for the atoms next to them. Those neighbors now have enough speed to climb their own hills and snap into place, which in turn releases even more energy for the next layer of atoms. This is the birth of the flame. It is a runaway feedback process, an exponential growth where one reaction triggers two, and two trigger four. Within a fraction of a second, billions of atoms are snapping together simultaneously. We call this a catastrophic chain reaction because once it gets started, it perpetuates itself. The fire doesn't need you to keep holding the match. The heat from the ongoing reaction provides the energy needed to keep the process moving. It is a self-sustaining loop of motion and attraction. As these atoms snap and jiggle, they excite the electrons around them, which eventually fall back down, and emit the light we see as a flickering flame. But where did the wood get all this carbon to begin with? To understand that, you have to look away from the ground. When we look at a massive oak tree, our intuition tells us a lie. We see the roots anchored deep in the earth, and we assume the tree is made of soil. It seems obvious. You plant a seed in the ground, and as the tree grows, it pulls its substance from the dirt beneath it. But this is the great misunderstanding of the natural world. If a tree were actually made of soil, there would be a massive hole in the ground around every trunk. The earth would vanish as the forest grew. In the 1600s, a scientist named Jan Baptist van Helmont decided to test this intuition. He weighed a pot of dry soil and planted a willow branch. For 5 years, he gave it nothing but water, and by the end, the tree weighed over 160 pounds, but the soil had lost only 2 ounces. The tree did not come from the ground, it came out of the air. Aside from a tiny fraction of minerals, the part that eventually becomes the ash in your fireplace, the entire mass of that tree is captured, carbon and water. Specifically, it is carbon dioxide that the tree has breathed in and processed. When you stand in a forest, you aren't standing among objects that grew out of the earth. You are standing among pillars of solidified gas and rain. The tree is a master of chemistry, pulling invisible molecules from the sky and turning them into solid wood. But this leads back to our atomic tension. If carbon and oxygen want to snap together into carbon dioxide because that is their most stable state, how does a tree manage to do the opposite? How can a plant take carbon dioxide, which is already a snapped molecule, and rip the carbon away from the oxygen? It requires work. It requires an immense amount of energy to force those atoms apart against their natural attraction. The tree cannot do this on its own. It needs a power source, an external engine to provide the force necessary to undo the stable bond. That engine is the sun. The sunlight hitting the leaves isn't just lighting the plant. It is physically hammering the molecules apart. The sun acts as a solar wedge, driving itself between the carbon and the oxygen. The plant keeps the carbon to build its body, and in a stroke of biological genius, it spits the oxygen back out as a byproduct. We call this photosynthesis, but you can think of it as unburning. If fire is the process of atoms snapping together and releasing energy, a tree is the process of atoms being ripped apart and storing energy. Every branch, every leaf, and every log is a collection of atoms held in a state of high-tension separation. They are waiting for a chance to return to each other. This realization transforms the very nature of what you are holding when you pick up a piece of firewood. You are not holding a fuel source in the traditional sense. You are holding stored sunlight. The tree spent years, perhaps decades, acting as a solar battery. Every photon that traveled 93 million miles from the sun to hit a leaf was used as a tiny hammer to drive oxygen away from carbon. That energy didn't just disappear. It was woven into the chemical structure of the wood itself. The energy is stored in the separation of the atoms. As long as those atoms are kept apart, the sunlight remains trapped in the substance of the tree. This is why the wood is so valuable to us. When you take that log and put it in your fireplace, you are setting the stage for a grand reversal. The carbon and the oxygen held apart by the work of the sun would much prefer to be close together again. They are like two magnets held apart by a powerful spring. The only thing preventing them from collapsing back together is that activation barrier, that hill they cannot climb at room temperature. But the moment you provide the nudge with a match, the spring is released. The fire, you see, is the process of the sun's energy escaping. The light and heat pouring out of the fireplace is literally the light and heat of the sun that went into the tree years ago. When you look at the orange glow of the embers, you are seeing recycled sunlight. The photons that fell on a forest in the past are being released all at once in the present. It is a beautiful symmetry. The tree uses the sun to build structure and store energy, and the fire destroys that structure to release the energy back into the universe. This cycle is what makes life on Earth possible. We often think of fire as a destructive force, a terrible catastrophe that ends the life of the wood. But from a different perspective, fire is just the completion of a circle. It returns the carbon to the atmosphere as carbon dioxide, making it available for the next generation of trees to breathe in. It is a continuous flow of energy from the sun, through the wedge of the plant, into the storage of the wood, and finally back out through the snapping of the atoms. But this process isn't limited to the fireplace. It is happening much closer to home than you might realize. If you look at your own hand, you are looking at the result of this same cosmic transaction. We often think of ourselves as fundamentally different from a flickering flame, but the chemistry tells a different story. The food you eat, the bread, the fruit, the meat is ultimately just another form of stored sunlight. Whether you are eating a plant directly or eating an animal that once grazed on plants, you are consuming carbon that was pulled out of the air by the sun's energy. Your body is a vessel for that captured solar force. Inside your cells, a process called respiration is occurring every second of your life. It is, in every chemical sense, a fire. You take in oxygen through your lungs and you bring it into contact with the carbon-based molecules from your food. The atoms want to snap together just as badly inside your mitochondria as they do in a woodpile. If they did it all at once, you would spontaneously combust. It would be a literal catastrophe. Instead, your body has evolved to be an incredible regulator. It manages the hill. Your cells use enzymes to lower the activation barrier just enough to allow the atoms to snap in a slow, controlled, and synchronized dance. Instead of releasing all that energy as a sudden flash of light and a roar of heat, your body captures it bit by bit, storing it in a molecule called ATP. This is how you stay warm. The body heat you feel is the jiggly motion of your own atoms, accelerated by the energy of the sun being released as carbon and oxygen find each other again. You are, quite literally, a slow burning fire. Every breath you exhale carries out the carbon dioxide that was once a part of your structure, returning it to the air so the cycle can begin again. This realization bridges the gap between the living and the inanimate. The same terrible snapping that creates the heat of a forest fire is the very thing that allows you to think, to move, and to breathe. We are not just observers of the energy cycle. We are active participants in it. But if the heat we feel is just atomic motion, what exactly is the light? Why does the catastrophe of fire produce that specific haunting glow? To understand the light of a fire, you have to look at what happens in the middle of the catastrophe. When those atoms snap together with such violence, the energy doesn't just turn into raw heat. It excites the very structure of the atoms themselves. Electrons, the tiny particles orbiting the nucleus, are kicked into higher, unstable orbits by the sudden release of solar energy. They can't stay there for long. As they fall back down to their original positions, they release that excess energy as a photon, a particle of light. The color of the flame tells you exactly what is happening inside that atomic jumble. Different atoms have different hills for their electrons to climb. If you throw certain chemicals into a fire, the colors shift. Sodium creates a brilliant yellow. Copper creates a haunting green. Strontium produces a deep red. This is the secret behind fireworks. We are simply choosing which atoms to invite to the catastrophe to control the color of the light they emit. Even in a standard wood fire, the orange and yellow hues are the result of carbon particles getting so hot that they glow, a phenomenon called incandescence. But even as the light escapes, something else is happening to the mass of the wood. As the carbon and oxygen lock together, they become carbon dioxide gas. As the hydrogen and oxygen lock together, they become water vapor. The solid log is literally turning back into the air it came from. The only thing left behind is the ash. If you remember the soil experiment, the ash represents that tiny 2-ounce fraction of minerals that the tree actually took from the ground. Everything else, the bulk, the weight, the strength of the wood has vanished into the atmosphere as invisible gases. This brings us to a staggering conclusion about the world we breathe. For billions of years, plants and ancient microorganisms have been performing this work, ripping carbon dioxide apart and popping the oxygen off. They didn't do this for us. For them, oxygen was a toxic waste product, a byproduct of their quest for carbon. They dumped so much of this waste into the atmosphere that they changed the chemistry of the entire planet. The very air that allows you to live and allows a fire to burn is the accumulated exhaust of 1 billion years of photosynthesis. We are breathing the leftovers of the sun's work. This leaves us with a final, staggering perspective on the nature of reality. We started with a simple question about why fire burns, and we found ourselves tracing the history of the atmosphere and the secret life of trees. We discovered that the world is not composed of static objects, but of systems held in a state of high tension waiting. The wood in your fireplace, the gasoline in your car, and the sugar in your blood are all examples of metastable states, boulders perched at the top of a hill, holding on to the sun's energy until the moment they are given a nudge. Fire is the moment that tension breaks. It is the catastrophe of the sun's work being undone. When you sit by a fire, you are witnessing a cosmic reunion. Carbon and oxygen, separated by the immense power of a star 93 million miles away, are finally allowed to snap together again. The light dancing on the walls is the ghost of the sunlight that hit the leaves years ago. The heat you feel is the physical evidence of atoms returning to their most stable, peaceful state. It is a return to equilibrium, a closing of a circle that began in the heart of the sun. But the story doesn't end with the flame. As the carbon dioxide drifts away from the fire, it doesn't disappear. It floats back into the atmosphere, invisible and weightless, waiting for the next leaf to catch it, somewhere. Right now, a tree is using the morning light to reach out and grab that molecule, ripping it apart once more, and storing that energy in a new branch. The stored sunlight is simply moving from one form to another, flowing through the air, the soil, the wood, and our own bodies in a never-ending dance of jiggling atoms. Everything we see, the forests, the fires, even ourselves, is just a temporary manifestation of this energy flow. We are made of the same atoms that make the stars, held together by the same forces that power the sun, and subject to the same beautiful laws of chemistry that make a match strike. Fire is not an ending. It is a transition. It is the universe's way of breathing. And the next time you strike a match, remember, you aren't just starting a fire. You are inviting the sun to shine one more time, right there in the palm of your hand.